Hi guys, how you doing? Hope you're all well. So in this video we'll be using the most popular IC ever created, any 555 timer. So if you're following along with my journey of my final year project, I need to learn about PWM chips so that I can use that to help charge the battery from the solar panel using a PWM solar charge controller instead of just a simple one stage or two stage charge controller. So since I need to learn about PWM, I figured the most basic version I could do is using a 555 timer to create, a PWM signal from a square wave. So in this video, what we'll do is we'll actually be just making a basic square wave using a 555 timer, as you can see here. So let's talk about it. It's a tiny, super cheap little IC used to create timers, oscillators, PWM signals, which if you don't know already, pulse width modulated signals, hence why I'm trying to use it today. So this thing here, it can be used in 3 different operating modes. That's basically a fancy way of saying that you can use it in 3 different ways. The first way is in its astable mode, secondly bistable, and thirdly monostable. You don't really need to worry too much about those, although I have found a really good explanation on Quora, which I'll stick on screen now. Pause it, give it a read if you don't know what astable, bistable, monostable mean. It was a bit confusing to me, but after I read this, I was like, you know what, that actually makes really good sense. And I thought, instead of me trying to explain it like that, just read this, it's worth it. Now, if you didn't pause it and you're hoping that I'd explain it, you're kind of in luck. So in this video, we'll be using the 555 timer in astable mode, which, if you look here, here's the output on the oscilloscope. So when you're using the 555 timer in astable mode, what that means is that the output of the IC is going to be constantly pulsing on and then off, on and off. So you can see here the output on the square wave obviously is just going high and then low, high and then low. So that's astable mode. The 555 timer is going constantly on and off in pulses. Monostable mode means that it's kind of stable. It pulses in single pulses when the 555 timer gets an indication from its trigger. So when you trigger the 555 timer, then you get a pulse. So every time you trigger, it shoots high. Every time you trigger, it shoots high. That's monostable mode. And bistable mode means that the 555 timer is flipping between 2 stable modes. But it's not like how it is in astable mode. It means that it's flipping more like a flip-flop. And so it flips to one stable mode, stays there. So it might go flip up, and then when you trigger it again, flip back down. So just 3 different modes that you can use the 555 timer. I will try to do more videos where I use it in different modes because I do really want to learn about these 555 timers in a lot more detail than I'm going to go into this video. But yeah, don't hold me to that. So like I said, read the description that I put on the screen from the Quora. The girl gives a good example, and it really did help me understand the difference. Okay, so like I said, in this video we're using the 555 timer in an astable mode, and we're using it to make an oscillator. So the circuit we're going over in this video is called a 555 oscillator. It generates a square wave, and that frequency can be fixed anywhere up to 500 kilohertz. So you can see here, I'm using mine at 1.5 hertz. So you can see, obviously if I had it at a much higher frequency, you wouldn't see the LED flashing. With these as well, you can vary the duty cycle from a minimum of 50% anywhere up to 100%. So it's actually very hard to get a duty cycle of 50%. I've actually got a duty cycle here of 52%, which you'll see in a minute when I go over it here. Now, I actually spent 2 days trying to get my duty cycle to look like this. It's actually very difficult, and I tried a bunch of different circuits. And to be honest with you, the only circuit I can recommend that you guys do if you want to make a square wave using a 555 timer is this one. There might be some other ones, but I tried about 4 or 5 different ones, and yeah, no success. But this one works really well. So you just literally just follow the pinouts, which you can see here, and then you just need 2 resistors, R1 and R2, plus a capacitor, and then you've got the LED with a resistor on the output. There are some other circuits where they have transistors and diodes, which I think is how you would get it to a perfect 50%. Like I said, mine's only 52%, but I want to keep it simple. I'm more interested in understanding the 555 timer itself. So what I do really recommend is the website I use to get this schematic here is this one, allaboutcircuits.com. They actually have a calculator on there where they use this schematic, or this wiring, schematic, yeah, schematic works. So they use this schematic with this calculator where you put in your capacitor value, your resistor value, and then they will give you the output that it's expected in terms of hertz, period, milliseconds, duty cycle, and then your high time and low time. So you can actually adjust your resistance values up here and then keep clicking calculate to get just exactly what you want. So I wanted a low frequency so that you can see the LED turning on and off. Obviously a high frequency, you wouldn't see that. And then I wanted it to be close to 50%. So I managed to do a 10 kilo ohm resistor for R1 and then a 100 kilo ohm resistor for R2. And then that gives me a 52% duty cycle. Go on their website, they have all the formulas that you use to calculate these basic stuff. Really, all of us will be able to understand that. So the way that this schematic actually works, or this circuit works, is the frequency of the wave is adjusted by changing these two values. So as you change these values, then you would then change the frequency and the duty cycle. So this capacitor here, you want to keep this one as 10 nanofarads because this is just to remove noise. So just keep this as a tiny capacitor basically. But this one here, the 10 microfarad capacitor, that's connected to pin 6. So pin 6 go into ground. Changing this capacitor will reduce the frequency of the square wave, which I'll show you in a minute. Changing R1, it will increase the amount of time that the output is high, right? So if I change R1, which is this resistor over here, as I change it, it will increase the amount of time that the output is high. Now, the important point about R1 is that by changing the value of it, it won't affect the amount of time that the output is low. So that means that if you increase the time that the output is high, it will just increase the whole period of the waveform, which obviously reduces the frequency of your signal as well. R2 is different. By changing the value of R2, it will increase both the high time and the low time, thus increasing the whole period of your signal. But obviously by increasing both the high time and the low time, so the time that it's on and the time that's off, you're then obviously importantly decreasing the duty cycle. Like I said, I do really recommend playing around with this calculator because as I played around with this, it really helped me get my understanding of how this circuit works. Okay, so let's go through the breadboard because I think that's always an important part of converting a schematic into a breadboard. So here's a breadboard, and I think I'm just going to remove a lot of these looping wires. I think it makes it a bit confusing to look at. I'm going to replace them with flattened breadboard ones. I think it's a bit easier. Okay, so just in case you haven't watched my other videos, in terms of the IC pinouts, it's important to know you've got to look at this little notch that you've got here and find it over here, there, and then you can map the pins from there. So pin 1 goes to ground, right? Pin 8 over here goes to VCC. So, and then just work out the rest, right? Okay, so I've got my supply coming in here, which is 6 volts, and then I've just got it jumping across to the other side of the board. I wish I had a proper board where I didn't have to keep doing this. I might need to buy a proper big breadboard. But anyways, so you've got the VCC coming in here, which then you've got it going to the IC pin, okay? Here then I've got a capacitor at pin 5 going to ground, right? And then I suppose we should probably go through. Okay, I'll kind of just mark it off for you, all right? So we've got here VCC, right, going up, pin 8 going to VCC. This capacitor going to ground, okay? Now the output is over here at pin 3. I've got a resistor here, and then going through to the LED, okay? Pin 1 goes straight to ground, which is this pin over here. Just go straight to ground. Pin 2, which gets a bit confusing. Pin 2 is just connected directly to pin 6, which I'll explain that in a bit. So pin 2 is here, this white one, going round to pin 6. Okay? Alright, now, the only other thing is pin 4. Pin 4 over here, going to VCC. Okay? This yellow wire here. Now this is where all of the magic happens now. So here now you've literally just got VCC, and then you've got R1, and then you've got pin 7, and then you've got a resistor, R2, okay, and then you got pin 6, you've got a capacitor, and you got ground. That's so, I mean, it's you know, this is what I love about this kind of stuff, that when I look at this, I'm like, this is confusing, man. When I first opened this up and found this website and I looked at that schematic, I was like, I don't want to do this. But it's just VCC, a resistor, you know, and then V out, right, R2, that's it. It's so basic, it's brilliant. And you know, props to these geniuses that come up with these circuits. Cool. So I've got VCC here. Then I've got a resistor R1, which is 1 kilo ohms. Or actually, this isn't actually 1 kilo. Mine is 10 kilo ohms, which if you remember from here, I've got 10 kilo ohms and 100 kilo ohms. So 10 kilo ohms and 100 kilo. Okay, so 10k and 100k. Okay, and then I've got a capacitor, and that goes to ground. And so you can see here these two orange wires. This orange wire here is pin going through to pin 7, and this orange wire here is going through to pin 6. And that's it. It's that simple. And here you've got a beautiful square wave. So if I now attach my oscilloscope probes here across this resistor for my LED, and we look at the oscilloscope, there you go, you can see we've got a lovely square wave. Okay, so let's just compare what I was expecting to get using a calculator with what I've actually got on the oscilloscope. So I'm expecting 1.49 or 1.5 hertz, and you can see I've got 1.5 hertz. It does fluctuate a little bit, but 1.5 hertz. I'm expecting a period of 685 milliseconds, and I've got 650 milliseconds. All right. There's nothing to do with voltage because obviously there's no voltage input here, but I'm expecting a duty cycle of 52%, which I don't know if I can show you on my oscilloscope. Let me see. Lovely. I love this oscilloscope to bits, man. So I've got a duty cycle here of 52.4%, and I was expecting 52.38%. Perfect. It's just brilliant, man. This stuff is fantastic. You know, it's really nice when the theory matches the reality perfectly. Like, just come on, man, brilliant. And that's with, like, you know, these 1% tolerances on the resistors. So I'm expecting a high time here of 358 milliseconds and a low time of 326 milliseconds, which, yeah, let's not worry about that. But yeah, you can see it matches perfectly, so that's nice. All right, so let's mess about with some of these values. So I've got a 10k resistor up here for R1. I've got a 100k resistor here for R2. And then I've got a 4.7 microfarad capacitor here. So in terms of the capacitor, increasing it will reduce the frequency. So I've got 1.5 hertz right now, okay? And I've got a 4.7 microfarad capacitor. Let's increase it. So I've got my box of capacitors here. I'm currently using 4.7. So increasing it, going up to 10, will reduce the frequency. So let's do that. And so all we're doing here is just taking this capacitor out and then putting this one in. Let's let it stabilize. There we go. So you can see here, it's gone from, you know, a much more faster square wave to now a much slower one. Okay, so it seems about 550 millihertz, so half a hertz basically. So just doubling my capacitor from a 4.7 microfarad up to a 10, that's taken my frequency from 1.5 down to 0.5. So reduced it by, you know, three times smaller, just by doubling the size of my capacitor. So let's increase this now from 10. We'll go up to, let's go up to 100. In terms of safety, you don't need to worry about these voltages. I've got a 6-volt input here. You're not going to have too high of a voltage, so you're okay taking out the capacitors and whatnot. Might be a bad habit to get into though. That's the only thing. So here now, look at how slow this is. The LED stays on for ages. Still on. It's gone off, so it's off right now down here. It's off, it's off. It's very slow. Okay, it's gone on for ages. So I don't even know if am I even going to be able to measure this. It's so slow. It looks like it's 10 times slower. So apparently 57 millihertz, which would be, if we was at 0.5 hertz, now we're at 0.05 hertz. So 10 times slower. And you can see, like, you know, the oscilloscope is proper boring to watch this signal. And so you've got a very slow beeping LED here, which I don't know, maybe it would be good if you want to stick this on top of one of those, I don't know, cranes. I don't know. I mean, it's kind of off for quite a long time, but still. Anyways, yeah. So that's what the capacitor does. So increasing it, the size of the capacitor means it takes a lot longer to charge up. So you get a much longer up time and down time, high time and low time. So let's go back to our 4.7 nanofarad capacitor. So we've got a much faster square wave there. And I'm just going to go down to 1 microfarad capacitor as well. So here's the 4.7 microfarad capacitor, taking it down to 1 now. You can see the LEDs going nuts, and the square wave is a lot tighter compared to 2. So much faster. So the capacitor will control the frequency, and so where we previously had a 1.5 hertz signal using the 4.7 microfarad capacitor, now with a 1 microfarad capacitor, we've now got 6 hertz, so 4 times faster, and you can see that from the LED. Alright, so let's change up the resistors. I'll stick back in our 4.7, so I've got my 1.5 hertz frequency now. So up here for R1, I have a 10k resistor. What happens if we increase this resistor? What we're going to do is we're going to affect the time that the square wave is high up here, but we're not going to affect the time that it's low. So increasing R1 is actually going to end up reducing our frequency. Right, so I'll replace this 10k resistor with a 100k one. Again, it's safe to just pull it out. Here we go. And so you can see we no longer have a 50% duty cycle anymore. The output is high much more than it is low. And so what we've got is we've got a 66% duty cycle where it's on, and then a 33% cycle where it's off. And this is with both of these values now being 100k. Okay, so let's go back to 10k and then we'll change R2. Okay, so we're back to 10k now, and we've just got our normal signal. So if I now increase this R2, which is currently 100k, and I replace it with a 1 mega ohm resistor, if you remember, increasing R2 is going to increase both the amount of time that it's high and the amount of time that it's low. So you're going to get a much longer period. The signal is going to be much longer. As you can see, it's off for a lot longer and it's on for a lot longer at the same time. But very importantly, it will decrease the duty cycle. Now remember, with this circuit, the minimum it can be is 50%. So where my signal originally had 52% duty cycle, by us increasing this resistor from 100k up to 1 mega ohm, so literally 10 times bigger, we're going to get much closer to that 50% duty cycle. So let's actually just see what it is if I adjust my oscilloscope. I'm guessing it's going to be about 50.6 duty cycle. But we'll see here once it's done. 50.4. Yeah, 50.4 duty cycle. There you go. So you can see now it's a much better 50% square wave, 50% duty cycle square wave. However, you have a compromise, and this is where the calculator is really good. You guys should use the calculator, because as you're messing about with your values, it depends if you want to have, again, a low frequency and or a short period. So here now we've got a really low frequency of 155 millihertz. But our period has gone from 0.6 seconds all the way up to 6.4 seconds, so it's much slower. But our duty cycle goes from 52% down to 50.4%, was it? Changes a bit, but yeah, 50.2%, so much closer to 50%. And that's it. That's how R1, R2, and the capacitor affect both the duty cycle, frequency, high time, and low time of the circuit. It's quite cool, really. That calculator they've got on the website is really good. I definitely recommend it. Alright, so I'm going to geek out a little bit now. So let's just move this breadboard out of the way. And what we're going to do is we're going to go now into the pinout. I think this is very important because ultimately this is the functionality of the 555 timer. And especially if you want to manipulate this circuit to do other things or do something different, you're going to want to understand the pinout. It is tough. Like, it took me a while to get my head around this. So don't worry about it if you don't get it first time. I'm going to try and explain it simply without all of the extra fluff, basically, which is what I try to do in all my videos. So the first thing I think is that if I explain the pin out in order, it doesn't really make sense because you need to know some of the pins in order to explain it. So I'm not going to go in order. I'm going to start in terms of pin simplicity. So obviously ground and VCC, hopefully by now everybody watching this understands what those are. So I'll start with the simple stuff and then we'll work our way up. So you've obviously got the ground pin, G and D, which is pin 1. That obviously just goes to 0 voltage ground, right? VCC, pin 8 is the supply terminal. It's obviously where you want to put your input voltage. Pin 3 is your output. So that's your output pin, which is this one here, right? My LED, pin 3. So let's go ground, out, and VCC. So probably the next easiest one would be the trigger pin. So pin 2 is your trigger pin. All this does is it tells the 555 timer to start running. Okay, I'm gonna geek out a little bit here, forgive me. I'll try and explain it. Okay, well, it's an active low pin. It's probably, if you've done Arduino stuff, you know what that is. What this means is that the 555 timer will start working when the voltage at this pin drops to below 2/3 of VCC. So it's not, you're not putting an input voltage in here in order to make the 555 timer turn on. You're doing the opposite. You're sending it low. So once it goes low, it doesn't have to go to 0 volts. It just has to go to below 2/3. So in my case, I've got 6 volts at my input. So once this voltage here drops to 4 volts, right? So once I get 4 volts at here, so let's say I keep it at 6 volts, but then I drop it to 0 volts, or anywhere from 0 volts to up to 4 volts max, then it will trigger the 555 timer to start working. This will make a bit more sense when you look at I'll show you the internal schematic of the 555 timer and where it gets its name from, and then it will make a bit more sense there. But there's basically a voltage divider. We're using a comparator in there to detect when that voltage drops to below 2/3. It's just literally just three 5k resistors. Okay, so that's pin 2. Let's go to pin 4. Does the opposite. It's the reset pin. What this does is that whatever the 555 timer is doing and wherever it is in its cycle, when this pin detects a low voltage, it will reset and restart the 555 timer. So again, just like the trigger pin, this reset pin is an active low pin again as well. Let's try and keep this clean. So you got pin 2 and pin 4. So pin 4 is also active low. So what it needs for this is it needs to be actually connected to VCC, and then you can send it low manually or using a microcontroller or whatever, or using Clever Electronics. You can then send it low in order to reset the timer. So what I can actually do is I'll just show this here. Let me just take off my oscilloscope output. So if I take this wire here, connect it to ground now, then if I touch this wire onto my pin 4, which is my reset pin, it will then reset the 555 timer. So let's just connect it to ground. And you can see there, so for example, if it's on, it resets. It's a bit hard to see. If I had a slower frequency or a lower frequency, it would be better. But you can see that I can manually reset it here. Okay, so the final 3 pins, let's go with the pin 7, which is the discharge pin. So for this, we're going to have to go back to the schematic here. So what pin 7 will do is, it's a bit weird and it will make sense when you see the internal schematic of the 555 timer. But look at this capacitor here. As this capacitor is charging up, when the output is low, then pin 7, it's a bit weird to get your head around. It will allow the capacitor to come up here and discharge through pin 7. Pin 7 here is connected down to ground. So this capacitor here discharges through to ground using pin 7. Again, if that doesn't make too much sense, I'll show you the internal schematic and I'll show you where it discharges through to ground. It just does that via a transistor. But think about it, right, like, you know, our capacitor is charging up and it needs a way to discharge, and so it's discharging through pin 7. Okay, so let's move on to pin 6, THR. Pin 6 is the threshold pin, or I suppose you can maybe put threshold voltage. So this has something to do with this capacitor as well. The purpose of pin 6 is actually to monitor the voltage across this capacitor. So what it's doing is it's checking the voltage across this capacitor. The reason why is this capacitor here, it actually controls the timing cycle of the whole 555 timer, so that when the voltage across this capacitor, again, this 555 timer uses kind of the same principle throughout. When this voltage across this capacitor reaches 2/3 again of VCC. So when this voltage reaches 2/3 of VCC, the timing cycle will end and the output will go low. Pin 7 is discharging the capacitor, and pin 6 is like watching the voltage of the capacitor. And finally, that leaves us with pin 5, which is our control pin, CTRL control. This is used to give more control to the timing cycle of the 555 timer. However, in our case, for the square wave, we're not actually using it because we're not controlling it. We're just sending it pulsing up and down. There's no control to it, basically. So what we're doing is we're just connecting it to ground, or we're leaving it floating. You could leave it floating, but that would introduce noise. So what you do is you connect it to ground. That could still have noise, so you just add a capacitor there. So we could put that it controls timing, but importantly in our case, not in use. So because it's not in use, we're just sending it to ground and sticking a capacitor on it so that we can remove any noise. And that's it really. I don't think that was too difficult, right? So I think now what we'll do is, once you've got this down and you're cool with this, let's take a look at the internal part and what is actually inside this IC. And this kind of blows my mind really, because if you think about the fact that like you just got this little IC here, but when you see how many components are actually inside this thing, it's hard to believe, because you're so used to resistors being this big, you're so used to capacitors, or there's no capacitors, but you're used to, you know, comparators are usually the same size as this. Transistors, you know, your big transistor, but this has a bunch of stuff in it. Now again, with my videos, what I try to do is I try not to be too technical, because I know for me, when I'm learning this stuff, it's frustrating when I watch a video and the person just goes into a whole bunch of maths and uses a whole lot of big words that I'm really confused, and is just like I have to go read a book as a prelude to watching their video. Like, that frustrates me. And so I kind of try to explain it in a way that someone who's brand new to this and just quickly wants to see what it is would get, if that makes sense. And I think, like, when I'm working on my car with my son, and you know, if I'm showing him stuff, I don't want to be like, this is the alternator, this is the cam belt, it controls the timing and the sequence of when the valves to the cylinder open and close. Like, that's just too much. So I just say, look, this is the engine, look, here's the engine. And so I'm going to kind of do that with the schematic. Let's take a look at it. Remember, you just got this little IC, right? So here is the internal of the 555 timer. So you can see here, here's the voltage divider that I mentioned, and this is where it gets its famous name, 555 timer, because it's just using 3 5k resistors to create a voltage divider. And then you've got comparators here, which are connected to see the 2/3 voltage, 1/3 voltage. You've got the discharge pin. Remember, I said the pin 7, it discharges the capacitor to ground. How does it do that? Follow the pin across here, this way, via a transistor, right? So when this transistor here is turned on, then it then discharges the capacitor through to ground. So pin 7 is connected directly to ground via that transistor, like I mentioned. You can see the comparator that I mentioned on pin 2. So pin 2, you have the voltage here. So this comparator here is comparing 2/3 voltage at this point here, so the voltage at this point here, and it's comparing it to this, whatever it's got at pin 2. And you can see there's a flip-flop here, which, if you remember SR latches from digital electronics, you've got the SR latch with the flip-flop, and so you've got the reset pin here at pin 4, which triggers that flip-flop and resets the 555 timer. And that's pretty much it. I mean, it's actually not too complicated, except for the fact that I'm actually kind of lying and I'm hiding from you the second half of this page, which this is the internal, you know, dumbed down version of what it actually looks like in here. And this is what I find amazing. So you've got all this stuff in here, right? In this pin, in this package, you've got all this stuff, but also in this package, you've actually got this. So this is this. These two are the same things, but look at that. Like, what the hell? If I'm honest with you, I've got very little understanding of how my engine works in my car. I'm just happy that I can drive it, and I'm happy that I can check my brake fluid. I'm happy that I know how to top up windscreen wiper fluid. As long as I understand my car to like this kind of level, I'm okay with. As for going this deep, this is quite deep. I don't have the knowledge to explain this to you, nor do I have the interest to learn this and understand this. I don't have the time, I don't have the interest. So if you do, great. If you feel like it, you want to explain this in nice detail in the comments for somebody else, feel free, man. I'll pin it. But yeah, so I'm going to suffice with this in terms of the basic 555 timer. I'm going to try and move on to using it in different operating modes, because I feel like it would just be nice to just get as much experience with this kind of stuff as I can before I move on to PWM. But I might move on to PWM as well. I think one thing I could do with this schematic here, which you can see, is you can see the 3 5 kilo ohm resistors there, right? You can see them. And so I'm guessing this is like a comparator, Okay, I don't really know how you combine transistors to become an op amp or a comparator. You can see here the reset pin connected to a transistor. I mean, I understand here the discharge pin, look, like I said, is just literally just connected to ground via one transistor, so that's easy to understand. But look, it's got a bunch of resistors. You got 100 kilo ohm resistors there, 4.7k resistor, 830, 4.7k, 6.8k. So there's more than just what it looks like here. Here it just looks like there's only 3 resistors in there, 5 but that's just these 3. So yeah, man, there's a bunch going on here, and all of that, madly enough, is in this tiny thing, which I think is incredible, man. I think human beings really are incredible. I'm not one of them, but I'm working towards it. So yeah, thanks for watching, guys. I'll see you in the next one. Take care. Bye bye.